Okay, we talked about migration. Now I want to talk about modernizing. I'm just going to show you an example. All right, we're not going to go anywhere near as much detail. Okay, this is also an aircraft application. Boeing has software called Boltstroke. It flies airplanes. Okay, they put it in a whole bunch of different airplanes. They put it in C-47s. Okay, they put it in fighter jets. They put it in helicopters. They want to put it in every airplane they build. It's a new kind of airplane they're building called UAVs. Okay, these new airplanes have a problem. They now have video in them. The old airplanes did not. Video takes vast amounts of bandwidth. Okay, the old software didn't take that into account. So the new software, so the old software they have can't deal very well, okay, with the performance demands of the video. So they needed to handle what's called quality of service, okay, inside the software, and the software didn't have any concept of it. Okay, so let's see, come on. So they had 6,000 components. There was a component made of a nose gear, a radar, an aileron tip, okay, and they'd screw these 6,000 components together to make an airplane control system. And they had to teach all these components about this QoS idea. And the way they do that is to rip the old operating system out, which didn't know anything about that, replace it by something called Corba RT for real time, which understands all this stuff. You have to find all the OS calls, replace them accurately by corresponding calls, and then you have to reshuffle the code, which has a bunch of APIs for communicating with each other in a way which is compatible with the way Corba wants you to do APIs. Okay? If you convert a module at the rate of 1 per month, do the arithmetic, okay, it immediately falls out of the boardroom. It's like, no, we're not doing this, okay, and then Boeing, somebody internally in Boeing says, we're not building UAVs because we can't afford to re-engine the software. This is not a good answer inside a corporation like Boeing. Okay, well, so we actually built them a tool to do this. Okay, I'm not going to go into the details, but it uses the same kind of rules we talked about, just uses lots of them. Okay, and went to see a live fire demonstration at White Sands about 1.5 years ago. Its UAVs are busy looking down on things that might be terrorist source, picking up the data, radioing it to a command center, which feeding it off to a jet to drop something nasty on that place so the terrorist goes away. Okay, and the video bandwidth controlled by this guy essentially was enabled by this kind of change that we made to the components. Right? Without that, they couldn't do this. Okay, so the last one is SOA. Right? Service-oriented architecture is about making the contents of your systems visible to the outside world. They own data. People want that data. They can't get access to it with the way the legacy technology was put together because it was built when the whole world was an island. Everybody has a mainframe. It's insular. You got a box. Nobody wants to be that way anymore. They want to talk to the rest of the world. How do you get access to the contents? Okay, so here's an application. We have a customer that builds embedded devices. Actually, you all know their name, but I'm not going to say it. Okay, these devices have to be configured, like your television set and your phone these days. But after you configure a device, if you're like me, you forgot how you configured it. So you want to be able to ask the device how you configured it, so you can configure it and then convince yourself you configured it right, and go back and revise it. So you need a way to configure it and ask. That's internal state. It's just like a database. Now the problem is if you have one device like this and you only have to configure it by hand, you could put one engineer down and make him configure it. What happens if somebody hands you 2,000 devices and says configure them all? You can configure them all by hand. This is just really not a smart idea. The device costs $200. Your guy costs how much? How long is he going to spend doing this? Not good. So what you'd like to be able to do is to be able to access the internal state variables of the application and make modifications using an outside interface. Okay. So we built a tool to do this by reading in the source code. This is like 13 million lines of C. These are big applications. That's why you could probably guess who they are. Okay. 500 products. Okay. This has 500 variations if you like. And for each of those variations, they want to be able to do this. 50,000 configuration commands. Okay. Again, do the arithmetic. Okay. You can't do this by hand. It even takes a week each. So you need a tool to reach into the code, find the configuration variables, generate an API to provide access to that configuration variable, and make that API visible to the outside world. This is the SOA problem. Right? Okay. So the way this is accomplished, very high level picture, read the source code, extract virtual screen images. This thing prints out screens of text. On the screen of text are holes where the configuration variables come out. Okay. And the holes that print out, the things that print out what's in those holes use the code that accesses the data. So if you know what the screens look like, you know where the variability is, and you can find the code that backs that up, the code behind that is the data, which is interesting inside the system. So the purpose of this step is to figure out where the interesting artifacts are. Okay, most people in an IT community have a database. It's there, it's database. In this case, these guys didn't even have that. Okay, so there's a screen. Okay, they'd like to be able to point to the screen and say, I want that variable. Okay, have the tool reach inside the code and find out what generates that thing. Okay, and pull the code out for that and manufacture a compilable API. And now you can add this, include this in the application. Now you have access to that particular thing. To give you some idea what this looks like, okay, imagine that that's, well, 12,999,000 something lines bigger than that. Okay, so this is a sample of the piece of code. So it says print things out like IP address, and if Q is true, then print a timeout, and pack count 0, print no cat. So this is the kind of code which is in there. This code gets processed by our custom tool. Okay, extracts a screen image, and it produces a piece of XML. The XML says the text that would come out when you run this piece of code is the following. It would print out IP address equals, and then would print out something. We call this a getter ID. This getter ID corresponds to that piece of code right there. So there's something it might print. There's another piece of variability. There's several pieces of variability in here. We're going to look at this one. So this produces a screen image and a set of selectable places. This step says I want to extract from the screen image. Oh, this extracts from the screen image and pulls out the places. So these are the internal states, okay, that are of interest. An engineer points at this thing and says, I want that. The tool says, well, that came from there because it's got this backtrace. Okay, and it generates an API. It says, here's a piece of code that would access what that variable is. So that process is completely automatic except for a manual selection step here where the guy says, I want that one. They're expecting to say, for all of these things, I want them all. Okay, they're only pointing at this point as sort of experimental. Okay, so we've seen a variety, okay, of different tools. I want to make it clear, I want to make it very clear that all these tools, or that DMS engine, configured in various different ways. They're all that DMS engine with a modest amount of engineering energy on top of that to achieve those what appear to be radically different tools. So the idea here is to build a tool that can generate the tools that you need to do your job relatively economical. I want to make it clear, it's not free, it's not easy, but it's a lot more practical than doing stuff by hand. Okay, so final conclusion. Legacy systems to me, they mean success. They're going to be around for a long time. Okay? You have to respond to the decay or you're going to cross that line of unmaintainability. You've got to actively, proactively enhance your system somehow. Good software process can help. Okay, it's a good idea to do that. If you're not, I highly encourage you to go out and do that, get partners to help you set that in place, whatever you have to do. Not us, not what we do. But you can get tool support to help you deal with that software process, to help you see into your code better, to help you measure the quality better, to help you carry off the automated steps you can't do by hand. Okay, that's where we can help. That's where we and our partners can help, okay, by helping you a combination of process and tools together. This is probably our key insight. Okay, if you go look at other vendors that sell you software engineering tools, they'll sell you 5 tools. And if you ask them how they built them all completely custom, by themselves, completely separately. Those tools have nothing in common. Okay, well, that's fine if you want to build tools slowly and painfully and over a long period of time. If you want to build a lot of tools, you need tool-generating tools. And this is the perspective we bring to the table. Okay, if you have a tool-generating tool, you can configure that and get the tool you need, okay, in a reasonable time frame, something that makes the process economical. Okay. Last thing, of course, is you can take these tools and configure them to carry out really sort of massive changes, Herculean changes, okay, to your source code, okay, with some effort, okay, to carry off migrations, mappings from platforms or languages to different platforms, modernization, find some piece of the subsystem and pull it out and replace it by something else, solarization, provide access to the internal state, okay, or other things which are not so easily described. Okay, everybody has some peculiar requirement about their system, about what they want to do, and they don't necessarily fall neatly into those bins. Okay, the tools that we build, we're okay with that. Okay, we understand what you want to do, and then we can usually figure out some kind of way to carry that off. All right, last point is, because the tools are automated, because we give them rules, we can run them reliably, we can test them repeatedly before we apply them, they minimize your risk in carrying out these kinds of changes. They're the things that make these sorts of massive changes survivable by an organization that's big.